Good morning.
Good morning.
So the first thing we are going to do is to talk about phase field approaches. Phase field approaches have come over from, I would say, the mathematics community, where they have been used to replace what they call sharp interfaces by diffuse interfaces. And essentially, it's the same thing as replacing a discrete description of a crack by a smeared description of a crack. In the mathematical physics community, they use these approaches also for many other phenomena. For instance, when you have two liquids with different phases which don't mix, the interface, for instance, between an oil droplet and the water is a sharp thing, which is then sort of described by these kind of phase field approaches. Well, the idea is essentially the following. If here we have something like a strain at the crack, which is described by a direct function. So here we have a jump in the displacements. So that means that when we differentiate that, we get strains which have a direct function. So many phenomena can be described by that. And the idea is that we replace this direct function by a continuous function, something like this. For instance, where here we have the shape of an exponential function. Obviously, you have to introduce a parameter which controls the width. And this parameter, which mathematicians have introduced as a regularization length, turns out in mechanical processes to have to be this internal length scale, which we also yesterday saw in many of these gradient damage models, these non-local damage models. So we have here a regularized direct function, which is a function of x, the ordinate orthogonal to the crack, and where the strain has this exponential function. Now, the important thing is, of course, the definition of a direct function is such that it is zero here, in principle infinite here, but the integral of the direct function over the domain is finite. So if we make it such that this finite integral is equal to the integral here, then we should have an equivalent problem. So that's the whole idea behind any phase field model. And, well, the exponential function is the most often used. You can also use any other function which obeys the property that the area below here equals the area here. And normally you will always need a parameter to control the width of this zone. And obviously, when L goes to 0, you retrieve back the original formulation. So the closer L is to 0, the better, the closer you approximate the original problem. The downside is, the smaller you have L, you essentially distribute the discontinuity over a finite width. And you have to resolve that with your discretization. So if you make this small, the area over which you distribute the crack is small. And you need a lot of elements, small elements, around the crack. So you resolve it better for small L, but you have to pay a price with more elements and therefore more computing power. So now we go a step further. So this is the basic idea. How is these kind of things implemented in practice? Well, in practice, this function is never used directly. It's rather used indirectly. So if you look at this linear second order differential equation, with these boundary conditions, it is 1 at the center and 0 at plus or minus infinity. Then this function, this exponential function, is a solution of this differential equation. Now, in many problems, or many solution techniques, like finite elements, we use rather weak formulations. We use integral formulations rather than directly the differential equation. So we convert this into a weak formulation. And here, when you look into this functional, well, here you see the first derivative, and obviously when you have this, when you multiply it with a test function and use Gauss integration theorem, you obtain the first order derivative. Well, that's nice. That means that as classical infinite elements, you have reduced the order, and therefore you can reduce the continuity which you have to apply. So the nice thing is, there are just first order derivatives here. So you can use normal shape functions, like normal triangles, normal quadratics, functions that have C0 continuity at the element boundaries, which means that the function itself is continuous, but the derivative is discontinuous. So this is allowed by this. This is one of the reasons to go to this function. You can go to other functions, but they may require higher order derivatives here, and therefore you get second order derivatives, for instance, here, and then you need more advanced interpolation functions. Now, the crack surface can be interpreted as this problem, when minimized, divided by L. So this integral is or should be the crack surface. Obviously, this is something which has a volume and not a surface. So the crucial point is, upon mesh refinement, does this converge to the discrete crackling? So do we have a problem which, upon mesh refinement, the smear problem really converges to the discrete problem? Now, one other thing. What you see here is you have the phase field parameter here, and you add gradients. Well, if you go back to one of yesterday's lectures, think of the gradient damage models. where you also had the damage parameter, where you added gradients in order to make the problem well posed. At first sight, this looks a little bit similar. And it is in fact quite similar. Now, you can do that, of course, in a this is one-dimensional. You can do it in a multidimensional generalization. And then this becomes, of course, this is the same, but now here we have the multidimensional gradient operator, which we square.
Excuse me.
Yes?
Please one slide. Here, can you please by this integral over L represents the crack surface?
Sorry?
How this gamma equals ID over L?
This is just defined like this, and it turns out that it is the case.
And while coming from like the second last line to the last line, how do we get this nabla d squared, the norm of gradient of d from that term?
Yeah. I mean, here I've gone a little bit too fast. This is the one-dimensional case,
Okay.
and this is the multidimensional equivalent. I mean, in fact, I should have had this line before that line. So this is the one-dimensional case. Now I want to go to a 2-3-dimensional case. And then I replace the gradient by this. And in fact, there's a typing error here. This should be ddx squared. Now, what is in the specific application to fracture, and in fact to brittle fracture? Van Voor and Margot have said, okay, we look at the total energy of a body, and this is composed here of the elastic energy in the body, plus here the fracture toughness integrated over the crack length. Just energy. And then we replace this, which is for a discrete crack, by this expression. So here we have the thing for a discrete crack with the fracture toughness here. Here we have the value, and this is the distributed value, which, like here, you have borrowed from here. So you can say this is a sort of the distribution of how this energy is distributed, orthogonal to the crack essentially. And then we can replace this, which is discrete. You want to get away from that. So you replace this line integral or surface integral by a volume integral, using this trick. Essentially you say, I have a discrete crack here, the energy you dissipate is Gc per unit cracked area. I replace that by Gc times gamma L as the energy that is dissipated per unit volume. And obviously this is, well, has something like this shape. So we now have two volume integrals. We can put them together, and this integral we have to take on and to minimize. So, for the case of brittle fracture, we have a potential energy, which is the part stored in the body, and the part distributed in the grid. Now you have to do one more thing. It's a bit of a trick. You have to say, okay, this is my, because if you propagate the crack, you get something like a degradation, a lowering of the energy in the reservoir. And this is modeled by multiplying the original elastic energy by a degradation function. Now, here it becomes a bit messy. I do admit that. This is a little bit where empirism, pragmatism comes in. So the beautiful mathematics is now gone. This is something like a fitting function, which, however, does have to obey certain mathematical continuity conditions. I mean, in the beginning, it should be 1. If everything is intact, when everything is degraded, it's 0. And you have also to have some requirements for the derivative of it. Now the energetic driving force is the derivative of the potential function with respect to the phase field parameter, and is the derivative of this degradation function with respect to d times psi. And here you see this one must obey certain continuity requirements also, and that's imposed on this. Now, the simplest possible, in fact, degradation function that is used is 1 minus d squared. Well, for d equals 0, so when you have no crack, gd equals 1. When d is 1, and remember the analogy with damage mechanics, then g equals 0. The derivative is 1 minus d. So that means that when d equals 1, at complete failure, we have no slump, which is imperative because at that moment we don't want to have growth of the phase field anymore. Then you must have something that at some point levels, and at the end of the process there is no growth, no slowing. This is one of the differences with gradient damage. Typically we have this 1 minus omega or 1 minus d, and there you get some differences. So here you see them together. Here you have what you would get for your driving force when you have gradient damage. Remember, this is your driving force. It's your dg dt. And in case of a linear function, like in gradient damage, dg dt is just minus 1. So here we have just minus 1 times the elastic energy. And that means that you have a constant driving force in these gradient damage processes. And that's the explanation why you have this broadening, which I showed you. I mean, you would want that the damage profile only propagates in this direction for this 3-point bending test. But instead, it also broadens. That is the consequence of this driving force. Here you see that the driving force in the phase field formulation is more convenient. Because when d equals 1, so at the end of the failure process, the driving force has gone to 0. So at the end of failure, we don't have additional driving and no propagation. Which is why, as I will show in an example, the broadening does not, in the wake of the crack, does not occur for these phase field formulations. So in that case, you have a constant bandwidth in contrast to these gradient formulations. On the other hand, in both cases, you have essentially, of course, your equilibrium equation, which you supplement with a differential equation to distribute your damage or your phase field parameter. I mean, you distribute it from a discrete line to a finite distance. And when you look into the differential equation that is supplementary in the gradient damage formulation, it's something like this. Now here we have our parameter which has the dimension of length squared. And look at here, we have the same here. Well, we have 4L squared here. We have the Laplacian of, in this case, the damage parameter, here the phase field parameter. So the left-hand side is completely identical, provided that we choose CG equal to 4L squared. And here we have D, the local value of the gradient damage, or of the damage, not gradient. And here we have, well, something that's a little bit more complicated. Here we have the length scale, here we have the derivative of G, and here we have a history parameter, and here we have GC. So it's slightly different, but there are clear similarities. You indeed see that they behave in a similar manner, but there are some subtle differences which make, for instance, that this broadening doesn't occur in phase field. And you see that here, this is a case where you have an initial crack. You have a step load here, so it's a dynamic problem. You get propagation along this initial notch, then further propagation, and at some point you even get branching. But you see that in the wake of the distributed crack, you have no broadening. Now, how do you solve that? Well, you have two coupled partial differential equations. The equilibrium equation and the equation to solve your phase field. Essentially not different from the gradient damage model. Always, or broadly speaking, you have two ways to solve a set of coupled differential equations. Either you do it monolithically, like I showed yesterday for the gradient damage model, that you assemble everything in a big stiffness matrix. You solve at the same time for the displacements and for the damage parameter. Or you do it in a staggered way. Staggered way means that you first solve the displacements. The values for the displacements give you a value for the damage, the local damage, or the local phase field. You feed that into your differential equation for your phase field as your load factor, your right-hand side. You solve for the non-local or gradient displacements or the phase field parameter. You look whether that's satisfactory. You go back to your equilibrium equation and you loop until you have Riesz conversions. Well, obviously, the staggered scheme is simpler to implement. It has a drawback. It's simpler to implement. You can also use, for instance, two packages, one standard package for your strength problem and a separate one, and you can, via a common database, iterate between them. Or the monolithic scheme, which is more difficult usually to implement, but has the advantage that it's a bit more robust. I show that here. Here we have looked at a simple case of a one-dimensional bar with an imperfection which we put in tension. Well, in the monolithic scheme we have something like this, where we have a neat snapback. So at some point not only the load goes down but also the displacement, because in this case there is so much elastic energy stored that you get a sort of explosive failure. And if you want to simulate that in a quasi-static manner, you can only do that by reducing also the displacement at the end. And the monolithic schemes are far from that, sorry, the staggered schemes are far from that, and it's very difficult to get here. You need very fine load steps, time steps in order to get it. So essentially, staggered schemes are easier to implement, are more versatile, but monolithic schemes are more robust and allow you for larger load steps or time steps. Where exactly is that depends on your boundary value problem, but this is sort of the broad message I want to give you. Now, I told you at the very first slide that this parameter L, which was introduced to regularize your Dirac function, was introduced by the mathematicians as a pure perturbation parameter, to perturb the solution. Now, if you do a simulation with that and vary L, you see that for a large L you have this, for a smaller L you have this, sorry, for a large L you have this red one. You have a rather low peak load and a ductile behavior. For a smaller L you get this, the black curve, and for a high L you get the blue curve. So sorry, for a low L you get the blue curve. So I told you in the beginning that the smaller you make the length scale, the better you approximate your original Dirac function. But you need then more elements. And you see also that, I mean, essentially you would have, we are simulating brittle fracture. So you would assume something that has here a peak, a sharp peak, and then goes down. Well, clearly the blue one approximates this the best. And when you make the blue one even, well, the L even smaller, you get something like this. And in the end, you really approach a real brittle fracture. But you need, of course, a very fine measurement. Here you also see that the results are sensitive to this G function, this degradation function. The red one is the standard quadratic function. But you can also use, for instance, cubic functions, which more closely reproduce a brittle failure. And you see that here, when you have a cubic function, you get something like this, which is much more linear elastic, brittle, than this rather ductile response. So the observations here are both L and G have a physical relevance. You must calibrate them. They are not just mathematical functions. They must be calibrated and have a real meaning. This is related to the width of your fracture zone, fracture process zone. This one is related to how well you approach your brittle fracture. Well, we have said at some point, I go a little bit back, we have said here that we approximate this line integral or surface integral by a volume integral. And that this crack surface is defined as this functional divided by L, and that upon mesh refinement, this expression for a smeared way should approximate the discrete. So we have looked at that, and a simple case, and actually we found that's not always the case. The reason is that you have some boundary effects at some point, and that this approximation function not always works that well. But you can come very close. Here you see that we have played a little bit around with this. Here we still have a 20% error, but here we come close to zero. So there are still lots of subtleties, and it goes a little bit too far to go to all these subtleties now. The field is in pretty much development. It's a development of the, let's say, the last, 15 years or so, and still very much being developed, and not everything is yet understood. Now, the following thing. Essentially, you have two approaches to fracture in computations. One is the computation of fracture properties. You compute stress intensity factors, J integrals. Based on those data, you decide whether further fracture occurs or not. If so, you propagate the crack by a certain amount, which usually is a bit of experience, and then you carry out a new calculation, usually a linear elastic calculation for this mesh. You compute new stress intensity factors or G integrals, and you propagate the crack you make a new mesh, etc. Essentially, this is a series of linear elastic calculations. The other way is a full nonlinear approach to fracture, where you include the fracture law in your whole calculation. So here the central thing in so-called nonlinear fracture calculation is that you try to simulate in a full nonlinear process the crack propagation. And usually you use cohesive zone models for that. Now, there are lots of cases where you can use linear elastic fracture mechanics, but there are also some cases where you can't. You can use linear elastic fracture mechanics primarily if fracture is the main source of energy dissipation. Usually you have some inelastic processes around the crack tip. But if the energy dissipation there is small compared to the energy dissipation due to fracture, then this can be disregarded. On the other hand, if this is not small, when you have a region with dissipative processes, which is large compared to the structural dimensions, that's always key to that. Is this zone small or large compared to the structural dimensions? Then you are usually obliged to go to cohesive zone models. And what is the essential difference? Well, the essential difference is that in linear elastic fracture mechanics, the energy dissipation is confined to a point. So you have here an open crack. Here you have a point where your energy is dissipated. Just ahead of that, your stress is singular, and then you have an intact intact material. That's different in the concept of a cohesive zone, also called the Dugdale-Barnum-Blatt approach, after the founders of it. Here you have an open crack, here you have a closed crack, and there's here a finite zone, a fracture process zone of finite length, where you have dissipation. For instance, in metals, due to plasticity. In materials like ceramics, for instance, fiber reinforced, concrete, rocks, due to microcracking, if they are reinforced with fibers, fiber debonding, breaking, and all these kind of phenomena. Now, like linear elastic fracture mechanics, the tensile strength is one of the parameters. Like in linear elastic fracture mechanics, fracture toughness or fracture energy is one of the fundamental parameters. There's one big difference where the fracture toughness is dissipated suddenly. In cohesive zone models, it is a function of the crack opening. So GC is now a function of the crack opening and is released gradually. Therefore, also the shape of the decohesion curve becomes an important parameter. And that's especially so when you go to brittle fracture, quasi-brittle fracture. So when you look into concrete, rocks, ceramics, these kind of materials, which roughly have a decohesion curve something like this, then the shape is a very important parameter for the outcome of your fracture process. This is much less the case when you're having ductile failure. So elastic plastic fracture in metals is typically having the curve which remains at the tensile strength for a while and then only drops. So this is a curve that has been used quite often, for instance, by Viggo Fergard, by Alan Needleman, John Hutchinson, and this is quite commonly accepted. It turns out that when you do calculations, that in such cases it doesn't matter so much for the outcome what the shape is. On the other hand, when you have more this materials which have more this shape, then it matters very much whether it is very steeply falling back here and then has a long tail, or whether it is falling back much more gradually in the beginning. Now, obviously, in all cases, the area below the curve, which makes the traction over the fracture a function of the opening, which is the fracture energy. So this area is a material parameter. This same like here. So it's defined formally as the traction over the crack at a point integrated over the displacement history, crack opening displacement history at that point. So you now have a discrete traction separation relation where you can derive the traction as the derivative of the fracture energy function with respect to the crack opening. And you can write this as the traction is a function of the crack opening plus some history parameter. And a history parameter is needed, again, because at some point during the process, you can have that the crack starts to close again. And then you have to memorize the value of Vn, the largest crack opening that has been attained so far. Because also here, you go down here, when you have unloading, you go, like in a damage model, to the origin here, you go back here and then follow again. But you then have to memorize this point. So it has the same role as the damage parameter in damage mechanics, or the plastic strain in the elastoplastic models. Only it's not a strain, it is a crack opening displacement. Now, I said already yesterday at some point, continuum mechanics, standard continuum mechanics, the standard Boltzmann continuum, does not introduce a parameter of the dimension of length. As a consequence, you get these ill-posedness things, but also it's impossible in a standard continuum mechanics model to reproduce size effects. Fracture mechanics is different there, because in all fracture models, either be it linear elastic fracture mechanics or cohesive zone models, you always introduce fracture toughness as an independent parameter. Now when you divide the fracture toughness by the Young's modulus of the material, you have something which is proportional to length. So by the fact that you have an additional material parameter, which divided by Young's modulus gives you a dimension of length, you have in any fracture mechanics model, you have a length scale, and therefore can describe size effects. In fact, when your length scale becomes much smaller than your structural dimension, the cohesive approach reduces to linear elastic fracture. Because if L goes to 0, in that case, your traction at the crack tip becomes singular. And you retrieve the classical stress singularity of linear elastic fracture mechanics at the sharp crack. I mean, normally, a cohesive zone model blunts the singularity. So in a different from linear elastic fracture mechanics, in a cohesive zone model, you do not have a singularity at the crack tip. You smoothen the thing. Of course, when this length goes to the limit of 0, then you retrieve the linear elastic fracture mechanics case, and you do get again a singularity. However, as we know, the energy dissipation remains finite, because, well, you here have your traction, which is essentially, you can then write as your fracture toughness times a direct function, integrated over the length gives you the fracture toughness. So it's again the direct function property which you gives you that the integral of the direct function over the length equals 1. That's just the property. Yes?
So I find this a bit confusing. Previously you said that the LEFM works if the energy due to the fracture or the crack opening is much larger than the inelastic dissipation.
Yes.
And now if we say that L goes to 0 or L is very small, that means GC is very small. That means the energy for crack opening, the total energy for crack opening is kind of getting smaller. And then how is
Yeah. GC is a little bit ambiguous. In linear elastic fracture mechanics, it's principally just the energy dissipated in fracture.
So open the crack.
In cohesive zone models, it also includes some of the energy that is dissipated in the other processes.
The inelastic.
Yes. That's a bit confusing, yes. So here I'm a little bit, I sort of start with something that is a little bit broader, and I reduce it at the same time to something that is the fracture toughness in a narrow sense. Because I assume that when bringing L to 0, also all the other processes, the other discrete processes, become much faster, smaller than the fracture toughness. Which is, well, essentially, this is a constant thing. But the other things reduce. And the total energy dissipation is the pure energy that is required at the fracture toughness to create a unit area of crack as the only inelastic effect. In this definition here, you lump all the other inelastic effects in it. So this is why in linear elastic fracture mechanics you better talk about fracture toughness. And in cohesive zone models, you better talk about the fracture energy that is dissipated. It's a fine but indeed important point. And I do admit that the distinction is not properly made often in the literature. And I also have the tendency sometimes to be a bit sloppy there. So the bottom line is when you look into the cohesive approach to fracture, the crack opening is a part of the constitutive relation. And that's not the case in LEFM. And in fact, you can also formulate a phase-field model for cohesive fracture. Now, let's go back a little bit. Well, we have to go back quite a bit. Yes. So, look at here at the expression. We have here two parts. The volume part plus the part over the crack. This is a constant. It's the fracture toughness. Really the fracture toughness. It's not dependent on anything. When we define the equivalent for a cohesive zone, this term is the same, of course, but here we have a fracture energy function which is a function of the crack opening or the crack sliding, can also do, and a history parameter which is the largest value of the crack opening which is occurred. So this is essentially the difference then. Well, the regularization is exactly the same. The approximation of the direct function by a regularized direct function is not different. So you plug this in here, and this part remains the same, and you replace this integral over the surface by, again, a volume integral, where here you have this regularized Dirac function, this delta L. And here you have a function, a fracture energy function, which is a function of a field V, which is the interpolation of this crack opening. Now, there are some subtleties. One of them is that you must ensure that your crack remains really orthogonal, that the line over which you measure your crack opening really is orthogonal to the crack, and you can enforce that by an additional approach here, and then you get, in the end, something like this, where here you have a double cantilever beam, you pull here and here, you have an initial notch, and, well, this is a peel test, so you have a glue layer here, and you get a propagation like this. Well, now this is even a peel test without glue layer, and here you have the propagation of your phase field, and here you have your propagation of the crack with the stress concentration here, and it's a concentration, which means that it is not a singularity. Yes?
So, how, for this approach, how do we in general estimate the crack direction if we have something like a composite with particle, which it is not known that it will be good?
Good question. I don't know. Work in progress. I mean, there are some, as I said, this whole field, it's becoming enormously popular, it's exploding. It's seen as an enormously promising approach to fracture because it's essentially a smeared approach, but it's mathematically sound and retains many of the features of original fracture mechanics in a transparent way. But there are quite a few questions. And yeah, what I show now on cohesive zone is in a sense relatively early work where we see that there are still quite a few question marks. I just want to tell you what is, this is one of the modern trends in computational fracture mechanics at the moment. And there are still quite a few questions. One of the questions is, for instance, this. We have, for instance, in this cohesive formulation, we have a three-field formulation. We no longer have only the displacements and the phase field, but we also interpolate the crack opening. And you have to do that smartly. Because the displacements, as I said yesterday, are always, because when you differentiate displacements, you get strains. And strains are the same order as the damage parameter or the phase field. So you must interpolate them higher than the phase field. So in this case, if you see that if you interpolate all these variables with the same order, you get some funny oscillations in the stress. Well, if you do it smarter, where you interpolate, in this case, the displacement field cubically, both displacement fields cubically and the phase field linearly, then you get a perfect smooth behavior. So this is things where I say, okay, this is just not ready yet for large-scale use, but it's quite promising. This is another problem. We have problems still with structured meshes, where we, even with the right interpolation orders, have some oscillations. So, what's the big thing about phase field approaches? It's an elegant approach, mathematically sound and elegant. It's enormously straightforward to extend it to 3 dimensions. And there it is very different from the discrete approaches I will talk about just after the break. There are question marks about the internal length scale and this degradation function. It was introduced from a mathematical perspective, but it has a mechanical interpretation. You have to calibrate it on tests. And as I alluded to, they are, and that's nice again, related to damage approaches, which gives you a sort of more intuitive physical feeling for something that was here in this way introduced in a rather mathematical way. And this is, I think, no. There's a bit more there. This issue of convergence to the discrete crack is not yet fully resolved. There's an issue of boundary conditions. The irreversibility which you impose is still a bit unclear what effect it has. You can do it for linear elastic friction mechanics, but not for cohesive fracture. There are a number of publications regarding multi-phase problems. For instance, a typical problem there is hydraulic fracturing. Don't believe too much the papers you read there. It is not resolved. So there are some approaches, but I think the good solution is not out there. So it's a hot research topic. Promising, but at the moment still of somewhat limited use, limited to linear elastic friction mechanics calculations. So, and this was indeed the last slide. We've now a short, I would say, 10-minute break, and then we go further with discrete approaches.